Hello everyone, welcome to our TESOL Global YouTube channel. This is our FPGA video series where we will explain different aspects of FPGA. We will provide different examples and demonstrate some projects. In the first part of this topic, we discussed about some of the major FPGA manufacturers, some of the common applications of FPGA, a generic design flow of FPGA projects, features of Altera or Intel Max Gen Development Kit, necessary softwares for this, and installation process. In this video, we'll show inverter example is Verilog code, how to simulate it, and load it in Max Gen Development Kit. The key FPGA programming languages are Verilog and VHDL. Verilog is a low-level language or get-level language, so a lot of engineers prefer Verilog. It is similar to C language, which is considered as one of the basic programming languages. In contrast, VHDL is high-level language. In Verilog, all data types, functions, and gates are available as primitives, or those are already part of the language, so it can be used straight away. Where VHDL requires the users to import packages to include necessary definitions and supporting functions, similar to the library files in microcontrollers. In our experience, Verilog is easier than VHDL, so we will use Verilog as our primary language. So we will use inverter as our first example. Inverter is also known as NOT GET. Here you can see the changes of logics for NOT GET. So when the input is 0, the output is 1. And when the input is 1, the output is 0. So here you can also see the truth table of NOT GET. Next, we have the Verilog code for the inverter, where the module is the inverter and we have A as the input and B as output. And assign is mainly used to assign the FPGA or the part of the FPGA which will use as not get. And at the end, we have to use in module. So we will explain the Verilog code and how the Verilog codes work in our next few videos. You can also see the test bench for the inverter. Test bench is mainly used for testing a logic. Test bench mostly use logics which are not synthesizable. In the inverter test bench, you can see again we defined the input as the resistor and the output as the wire, and then we just map this with the real Verilog code and we put some timestamps so that the simulation can understand where it will change the state. So as I said, we'll have more explanation of this kind of test bench and Verilog codes in our next few videos. We will now see how to implement inverter logic in Modelsim and Quartus. Then we will generate its bitstream to upload the programming files in Altera or Intel Max Gen Development Kit. Before going ahead, we would like to ask you to subscribe to our channel if you are benefited from our content. Also click the ring bell so that you'll get the notifications whenever our video is out. To start with, let me open the Modelsim application. So this is the startup window for Modelsim. So from here, you'll have to go to the file, then new and project. It will bring up this pop-up where you need to enter the project name. So let us give the project name as inverter underscore test. Then it's asking us to where to save the project or the location of the project. So we'll already created a folder in the desktop where we'll save this project. So here you can see we have the folder projects and we created two folders. One is for Modelsim and one is for Quartus. So we'll select this folder, Modelsim 1, and our default library name will be work. So we'll keep it like this. So now if you press OK, it will ask you to add items to your project. So now we will add items to the project. So to do that, first we'll have to create the file, and here we'll create the main project file, which we are going to name as inv, and it will be a Verilog file. So we'll keep the label as the top level because this is very basic program. So now we'll press OK. So we can also create the test bench file here. So again, we have to create new file, and from here we can just write T inverter or T in, and we'll select it as Verilog file as well. So it will also be a top level because, as I said, it is a very basic program. So we'll just keep all of this as top level. So now if we press OK, it will also create another file. So now we'll just close this, and here you can see our inf.v, which is the main Verilog file for the inverter project, and we have tin.v, which will be our test bench. Now if you just double click the inf.v, then here it brings up this pop-up which is asking us to select from these options. So the thing is, you can also face this problem. So if you face this problem, then you have to find the Modelsim exe so that your next projects will be open in the Modelsim directly. So here we selected Modelsim, and we'll select always so that it will always open in Modelsim. If you do that, then it will again bring up this, and it will open your project like this. The problem here is we cannot see our working directory here. So let me just cross this and quit this one, and we'll work in here which we created or which we opened earlier. So now if you double click the in.v file, then you can see here it opened in a separate window. So we also face this problem few times. In normal situation or by default, when you click the in.v, it should be open in a separate window in Modelsim. But if it doesn't open, and if it open like the previous window where it was asking you to select the application, so you can just find the Modelsim exe, and then you'll just make it always open in Modelsim so that whenever you'll open next time your projects, it will open in the Modelsim window. So now we'll just copy the code we showed earlier to our working window. So this is the code we already showed. Next, we'll add our test bench. So before going to that, here for the Verilog code, you can see we just added a module which is inverter. We have A as our input, B as our output, and we assigned the NOT gate as the application for this project, and we just do in module. So we'll have more explanation of the Verilog course in our next few videos. Next, to go ahead, we'll just double click the T inverter, which is our test bench, and we also have already showed this code. We'll mainly copy this and paste it here. So now this is our test bench for the project where we assigned the input and output, and we just link the input output with the Verilog code we created earlier. Here you can see here we declared the input as a register and the output as a wire, and here we are just linking them. So this A is defined in our project file, which is in this file. You can see here we've defined input as A and output as B. So in the test bench, we define them as T underscore A or T underscore B, and here we are just linking them. So the simulator will know which is the input and which is the output in this case. Here we also give some time delay so that the simulator can also work properly or will know when the state should be changed. So here in every 5 picosecond the state will be changed. The first state here will be 0 and then we'll give 1, and then in the next we'll give 0, 1, and this way the simulator will understand when to change the state so the NOT gate can work properly. So now if we click here and go to the compile and you compile all, the Modelsim will compile our code. You can see the green marks in both of these. It means the code is now compiled and we can now simulate it. Now if we go to the library, these two files we just created and we compiled, this should appear in the work folder, but you can see the work folder is empty. The reason for this, we didn't save our Verilog code and the test bench. Now if you click save and also if you go to the test bench and if you click save, then if you just compile them back, then you can see the green tick again. And now if you go to the library, you see the work folder is not empty now. It has our inv and the test bench files. So now to simulate this, you just click simulate and it will bring up this windows. So from here, we'll just add this to waveform and this one as well in the waveform. And from here, if you just run this, you will see the simulation is working. It's very small, so you can zoom it. So zoomed it too much. So here you can see in every 5 picoseconds the state is changing. So here you can see first the input is 0 and the state is 1, and then if we bring it here, the input is 1 but the output state is 0. Next, if we bring it here, you can see again the input is 0 and the output changed to 1. So this verifies our simulation or what the gate is supposed to do. So now from here we can stop the simulation, go to simulate and end simulation. It will quit the simulation and we can also close the project and close the Modelsim window. We want to quit. Yes. So now we'll work on Quartus. So if you double click the application, it will turn on the Quartus application. And if you are opening it for the first time, it may ask you about the license and you'll just select it as free license. Now if we select the new project wizard, so here we click next, and here it's asking us to select the directory of the project. So you already created a folder in the desktop, so we'll just go to the desktop and here we have the projects Quartus and we'll select the inverter test project. Here we'll select this folder and we'll give the name of the project as inverter or inv, which is the same as we gave before in the Modelsim file. So now we'll click next. It is asking us to select the project type. We'll select it as empty project, which will create mainly a new project. So we click next. It's asking us to add files. So here we can add the Modelsim Verilog file for the inverter we created for Modelsim simulation. So if we go to our folders, from here, if we go to the Modelsim, here we have the main Verilog file. We'll mainly copy this and paste it in the Quartus working folder. So we also have the test bench, but do not copy the test bench because this file is not synthesizable. So if now we just copy this in this folder and we can add this, just have to go to the desktop projects Quartus inverter test and we'll just select this folder, which will add the inverter Verilog file to the system of the Quartus. And if you click next, here is asking us to select the FPGA we want to use. So we already know the name of the FPGA. You can see in the sub window the name of the FPGA. So we wrote it somewhere. We'll just copy and paste it from there. So just paste it here and it will give you that FPGA. Just before going ahead, just make sure this is the FPGA you are using. So now if you go to the board here, just unselect this, go to next. And here for the EDA tool settings, we'll keep it default. Now if you go to the next, it will bring up to our final window. Here you can just check the options and then finish it. Then it will create the project. Here you can see we have the inverter, and if you double click, here is the inverter code we already created. In many other applications, you can create your project directly to the Quartus. So there are some projects where it will be very big to simulate in Modelsim, or maybe it will not be synthesizable in Modelsim. So you can do it directly in the Quartus. So now we will compile our project. So if you just start here, it will start compiling and it will start synthesizing the codes. It will also create the bitstream which we will upload in our FPGA board. So it will take some time. You can see is the process is going on. So now this is done and you can see there is no errors in it. So next step is to upload the code in the FPGA. So now you can see the FPGA board in the sub window. So this is the power plug of the FPGA board. We already have powered it up. You can just turn it off and again you can turn it on. So this is the USB port to load the program in this FPGA board. So now if we just bring up the user guide and if we go to the block diagram of this board, you can see this is the USB blaster port, or this is mainly the port through which we will upload the program into our FPGA. So this is the USB blaster port. Now to upload the program to the FPGA, we'll just click the program device and it will bring up this window. So here you can see in this window, in this section, we already have USB Blaster 2. So this is because we already connected this FPGA to our computer before. But if you are doing it for the first time, then you will see this section is empty or there is no device mentioned here. So the reason for this is that the driver is not installed properly. So you have to install the driver separately. To do that, you have to go to the device manager, and here if you just go to the JTAG cables, you will see these two. If the driver is not installed properly, then from here you have to install the driver or update the driver, and you'll just browse my computer here. So to do that, you have to just browse and go to your installation folder for the Quartus, and from here if you just go to the Quartus, then drivers, and you'll just select this USB Blaster 2. If you just click OK, and then next it will update your driver, and then you will see in the program your USB Blaster 2 will appear. So already have done this, so we are not going to do it. We just showed you the step how to update your driver. So next, before uploading the code, one thing we didn't do is map our pins. So we synthesized our inverter code, but we didn't assign any pin for that, or like which will be the input pin and which will be the output pin. So to do that, if you go to the assignments and then pin planner, it will bring up this window where all the pins are available. So now you have to know like where you want to map your pins. So to do that, again, if we go to user guide, here you can see, if we just zoom it, here we have this push button switch which can be used as input. So you need to find in which pins these push button switches are connected. And we also have these user LEDs which we can use as output. So to find that, if you just go down in the user guide, here again you can see it's showing we have these push buttons which are the user push buttons, and we have these LEDs which are the user LEDs. So we have to find where these are connected. So if we go down a bit, now if we come to this part, the general user input or output, here you can see the pin number for FPGA for this signals or for this component. So here we have the push button signal names, and also we have the LED names. So we'll use this D15 or T20 pin of the FPGA, and we'll use, for example, we can use the first switch or S1, which is L22. Now we have to define this 2 into the pin assignment part. So if we go to the pin assignment, And here our input, we will just try to find it here. So our pin for the input, which is the switch, is L22. I'll select here. Here you can see the L22, which will be our input, and our output will be the LED, which is T20. So here if we go to the pin assignment again and select T20 here, I have to go down, and this is T20. So our input is L22 pin and our output is T20 pin, which we found from the user guide. Now you do not have to do anything here. If you just come back here, you can see again here you have the question marks, which means you change the pins. So now again you have to compile the code. So you'll compile it. It'll take some time to compile. So the compile is done and there is no error. So again we will open the programmer, and now we will upload the program. So if we just click start, so it's showing failed. One of the reason for that can be, if you see here, the name of the chip is different. So to solve that, you can auto detect your chip. So you also face this problem for the first time. So our chip is mainly this one. So we'll just select OK, and now you can see it just selected your chip automatically. So please remember to do this, otherwise you might not be able to program your FPGA. So now we want to load the program into our this FPGA. So select here, and it's asking us to which file you want to upload. So to do that, we'll just go to the desktop where we have our program. So here we have the program. So you can select this one, and now you'll have to click this. Now if we start, you can see now we have programmed it successfully. Here, this was the LED selected. So it's on because the input is 0. So our switch 1 is this one. So now if we click this, you can see it's 0. So when the switch is 1, or when we push the switch, the LED is off. So it means switch 1 output is 0. Now if we just remove it, you can see the LED is again on. So this is the LED we are working. So again, if we just click it, you can see the LED is off. So when the switch is on, the LED is off. If we just remove our hand from the switch, so the switch is Now 0 and the LED is 1. So this is the end of this video. In our next video, we'll learn more about Verilog coding and how it works. Please subscribe to our channel for more videos like this. We'd like to thank those who already subscribed and helping us to grow our channel. Add likes, comments, and give us suggestion of what kind of video you want us to make. Follow us on LinkedIn, Twitter or X, and in Facebook. Thank you for watching. See you next time.